of a colonial pattern which is observed in the a kind of bacteria, Bacillus subtilis. And from the 1 point inoculation, I showed 5 different patterns depending on the environment conditions. This is softness of agar. This is concentration of nutrient. And in order to understand, we propose the mathematical model which is described by the quite simple reaction-diffusion system. And basically, this model described by only 2 variables, B and N. And B is the active phase cell, and W is less active. But this is just equation for that B and N. And if you can solve this equation and putting here, then we can get W. Or by using this initial condition, W is given by this one. Just sort of the integration of this from 0 to T. Okay, this is quite simple reaction diffusion equation. And also we have a very perfect answer on the asymptotic behavior of solution. It means so B tend to 0 and W tend to W infinity, and nutrient N tend to some constant. Okay, so this is very perfect answer to show the asymptotic behavior. But this is really mathematical result. But if you are interested in the biological problem, this information is not enough, because the important thing is the following. So B plus W, this is the total density of cells. And by using the previous result, B tend to 0, W tend to W infinity. That's why final spatial pattern is given by this one, okay, or this one. Okay. And then by using numerics, we observe quite different patterns depending on the parameters. Okay. The question is, how can we prove this kind of very diverse colonial patterns? This is not easy, because look at this equation. This is the equation. So in order to know W infinity of X, we have to know the almost whole interval of B, N in time. Okay? Of course, B and N asymptotically tend to some constant, especially B tend to 0. So asymptotically, very simple, but intermediate time, so say 0 plus maybe some capital T, that gives us sort of the information on W infinity. So in order to understand W infinity of X, we have to discuss about the transient behavior of B and N. Okay, this is very much difficult part. Okay. So a message from our reaction diffusion system to us. The system looks so simple. However, mathematical analysis has just started. So now, unfortunately, we have no clear result on W infinity X. Okay, because we have to consider the transient behavior of B and N. Okay, so there's no mathematical tool to understand such a process. Okay, So this is a sort of story which I wanted to talk yesterday. And today, maybe you remember this picture. I would like to discuss another bacterial colony which is observed in the E. coli. So this is okay. So this is okay. I have to say this is sort of the artificial colorize, okay, for the audiences to enjoy. But actual, I mean, the one is like this, just like almost monotone. And this part, small, I mean, the cluster is we call microcolony. And the location of microcolonies is showed something like a very interesting pattern. Typical, I mean, the characteristics of a pattern is so like this, okay? So like this. That's why we call this kind of pattern is chevron-like pattern. And now I would like to, I mean, discuss about this kind of pattern. Why E. coli generate these very funny patterns, okay? Okay, and then yesterday I briefly showed some paper. This is so paper, and Badley and Bag, the experimentists, proposed two papers, 1991 and 1995. And this is the first paper, maybe first paper, and the title is Complex Patterns Formed by Motile Cells of E. coli, okay? And the essential difference of this bacteria from the previous Bacillus subtilis is this E. coli has a sort of property. It's called Chemotaxis, okay? And the Chemotaxis means maybe it's better, means the following. They recognize a kind of chemical attractant, okay? And they change their way how to move depending on the concentration of attractant. On the other hand, each E. coli produce a secret, a same material attractant, okay? So for instance, if there are two, okay, and then if this guy produce or secrete some chemical attractant, then this guy moving this way, in some sense, okay, move here. So I mean, so this may be two. So secrete a little bigger. So other is coming like this, okay? So probably you may expect the occurrence of aggregation intuitively, okay? And then skip one here, okay? And then the first, I mean, the result done in 1991 in the first paper, they emphasize the following. Depending on the concentration of nutrient, the colonial pattern, I mean, the change their form. For instance, this is 1 millimole. At that time, this is inoculation here. So it's very nice disc shape. We say this is obvious or a trivial pattern. But when we change this one from 1 to 2, so we have a drastically changed pattern occurs. And the characteristic of the pattern is like this, okay? Or like this. Just this, I just draw this one. And interest point probably here. Look at here. If this distance, okay, so distance is wider, so the new cluster appear. Okay, so maybe you can see here. And they keep the almost same distance, okay? But the characteristics is like this, almost, I mean, I should say synchronized, okay, way. And this is 2 millimole, and just I explained yesterday. And if it is 3 millimole, is basically same, but this is alternative, okay. So it's quite, so this is almost this direction, but this is here, this alternative here. So depending on the concentrations of nutrient, E. coli change their pattern, okay? And in order to understand from experimental as well as theoretical point of view, at first we want to know how single cell move, okay, depending on the concentration of attractant. Okay, so, oh yes, and maybe yesterday I explained the basic, I mean, the mobility of E. coli by using the flagella is they use 2 ways, running and tumbling, okay, and then so like this, okay, yeah. So this is a basic, I mean, the movement, okay. But interest, oh, sorry, so this is wrong. But the interest following, okay. If this is wrong, okay, this is the center, okay. If some, I mean, the chemical attractant, so in this case, aspartate, okay, supplies on the center here, for instance, okay, then many, I mean, the E. coli is moving toward the center. Okay, so you can see a kind of aggregation. You know, so this is just center. Okay, but interest point following, they check the mobility. The result is the following. This axis is a distance from the center to some point. Okay, yeah. And this axis is a tumbling frequency. How many times they change the direction per unit of time, okay? And the result is the following, the almost step. What does it mean? This means the following. In this area is a relatively high concentration of attractant. In that situation, tumbling frequency quite low. Okay, it means they prefer to run. Okay, but if this area, it means quite a low concentration of attractant, at that time frequency is very high. So like this. Okay, so it's very surprising for us is the following. Each bacteria cannot move toward a higher density of concentration of attractant. They don't do that. Only they change the tumbling frequency. That's all. It's very surprising for me. Okay? So no direct mechanism of direct movement. So please, I mean, remember, E. coli, even he or she, I don't know, has a chemotaxis property, they cannot move directly to the attractant area. Only the change the frequency of tumbling. That's all. Okay? Okay, in here. Okay. So I will show Okay, this is very, naive question. Can cells in a population level aggregate to the region of higher concentration of attractant? Okay, each cell cannot do that. Okay, but if you look at population level, can you aggregate? Of course, I will show aggregate. Okay, okay. And we propose a kind of model. It's so-called individual-based model. Okay. So this is the running and change tumbling, and then moving, running, so like this. But the probability of the tumbling frequency really depends on C. Okay. C is a concentration of attractant. We just follow the result obtained in experiment. Okay. And then I will show the following. So this is in our the domain, a square domain, and this region is a high concentration of attractant. Okay. So you can see this is like this. Okay. But here is almost running. Okay. So this is for probably this moving here. I don't know, like this, and quickly coming back like this, and so like this. So this is a sort of the simulation of our, let's say, microscopic model. And then, okay, but anyway, so maybe it's better next one. How about this one? Then the result is the following. Maybe it's not so easy, but you can see it's a sort of this is becomes dark. Okay. So it means so moving here and turn is like this and like this, and for many times, so maybe it will become dark and dark. Okay.
So this is simulation.
This is simulation. This is simulation of an individual-based model. And if this is just single cell, but if maybe 10,000, for instance, so it's a high density. Okay. So this is a sort of the result for E. coli. Okay. So now let's move to a more theoretical one. And at that time I have to mention the following. This is easy to say. There are three different levels. One is a microscopic level. This is like a micron. Okay, so like this one. And each bacteria cell moves, grows, and performs cell division. Okay, and the second step is a mesoscopic level. So mesoscopic level is just a microcolony. So I told you maybe microcolony, one microcolony consists of 50,000. So just this millimeter, roughly. And the third one is a macroscopic level. This is a centimeter, like this. Okay. So, so collective cells exhibit ordered pattern, as if these were controlled by somebody. Okay. So it's clear to see three different levels. There's a micro, mesoscopic, and macro. And we are interested, in this talk, we are not interested in this one. We are interested in this one, macroscopic model, in order to know this kind of pattern. Okay. And then this is a sort of a paper. This is the second paper, and at the end of their paper, maybe in the conclusion, Badley and Berg say the following. Yes, there are four elements. It's very clear. Okay, sort of consumption of nutrient and also cell growth, and also they secrete the attractant. And they recognize or detect the attractant and move. Okay, it's so-called chemotactic motility. It's very clear. But where these are combined in a certain way, bacteria could generate a complex spatial structure. And the important thing, they said, a specialized morphogenetic program is not required. They couldn't find a sort of a genetic element. Okay? That's the key point. However, it is still unclear genetic control or self-organization. Okay? And our standing point is to support this one. Okay? Okay, now our purpose is to propose a macroscopic PDE model, because this is the PDE School, which generates these patterns in a self-organized way. This is our purpose. Okay? In order to propose a model, this is a sort of suppose this is the bacteria. So it's 1, 2, 3, 4, 5, 6, 7 like this. Okay. So this is the number of bacterial cells. But in our model, we cannot do that. So suppose we consider some unit area, and we just count the biomass. Biomass is okay. This is maybe this is almost half, or this is half, or this is almost 1. So maybe in this case, this is maybe 2 or something like that. This is biomass. We cannot count the number. Just we count the mass. Okay. So this is and if this is the unit area, then this is a density of bacterial cells. Okay. So our target to study the time and space evolution of density of bacterial cells. Okay. Of course, we have some demerit. Demerit means if we use this variable, we don't know how many number of bacteria and when each bacteria performed cell division. We don't know. We only know the sort of the density. But nevertheless, we know the sort of pattern. If high density or low density, if you know this balance, so okay, high density means the sort of the aggregation. That's why by using the density of bacterial cell, we may know the colony patterns. Okay, that is our idea. Okay, so first step is we have to propose a model of chemotactic movement. And that was already proposed by Keller and Siegel in 1970. And they introduced one variable is U. This is population density. And C is the attractant concentration. Okay, and then this is their model. So U is a density, and this is just a diffusion term, and this term is a chemotactic term. And we can rewrite this part like this. So it means this is sort of advection term, okay? But sorry, this may be divergence is better, I think. And if this is some constant, for instance, so the velocity of this term is given by the gradient of C. Okay? So this is sort of the chemotactic advection due to the gradient of C. So it's okay. So don't confusing. I told you is that if you look at only the single cell, so single cell never ever move in a advection way. Only the funny diffusion. But if you look at population level, okay, then we have a sort of advection term. Of course, we have to check the relation between the microscopic and the macroscopic. But this is not so easy. But in United States group is Hans Osman, also in Germany, Angus Stevens. They are doing a sort of the relation. They are studying a relation between them. But now we just I don't like to touch with this. Just we are interested in the PDE model. Okay. So this is so if C is a given, then this is given. So this is just linear equation. Not so difficult to analyze. Okay. And then this is sort of the candidate of chi C. Chi C is here. Okay. And the importance is a derivative chi. Okay. But so many. But if for the simplest case is chi C is just linear, so this is like this. So this is constant, positive constant, and this is advection term. But advection term really depend on the gradient of C. So very simple. Okay. Okay. The second step is if C is unknown, it means following. So this is the same one, but if you produce C with a constant rate alpha, for instance, so this plus alpha u, this is sort of the production term. And what it is? This is sort of the degradation term or loss. Okay. So this is very simple. But nowadays, this coupled system is called Keller-Seigel model. Okay. So the system is no more linear because this is really quasi-linear parabolic equation. Okay. And also system. Okay, so it's not so simple. Okay, so this is a second step, but we don't have any growth term. Okay, but in that experience they eat nutrient. Okay, so this is also enough, not enough. Okay. And the third one is a model of chemotaxis movement with growth. At that time, we introduced a third variable N. So this is nutrient. And the equation system is given by the following. So this is the same one. This is the same one as the second model. But here we have a new. So this is a growth term. Okay, this is growth term. Okay, and this this is a nutrient equation. So nutrient is that diffusing, and this is u take n. So this is minus, and this is omega. Of course, or we may put it there, but this omega is a conversion rate. Okay. So a little bit difficult. Complex system. 3-component system for N, U, C, N, and this is a positive, and alpha, beta, and omega is a positive, also positive constant. Okay, so this is a starting point, but this finally I can do. This is not enough, but this is. But I have to say that model proposed by many groups. Okay, so earlier studies by mathematical modeling approach. This is United States, Bruno, and this is I cannot pronounce. This is the Israel group, and this group is Oxford group, and this group is Japanese group, and this group is Russian group. So all international, okay. So it's very highly compete, okay, to understand such a pattern, okay. It's a very strong competition. And then they say the following: they surely confirmed that the chemotaxis effect possibly generate spot pattern like this. It's so-called chemotaxis induced instability. Okay, so all of the model show the occurrence of spot pattern. However, as far as I know, they did not argue the mechanism of regular arrangement of spot, particularly chevron-like pattern observed in experiments. So they didn't discuss about the sort of a geometrical, the configuration of spot pattern. And this is one of the, I forgot, but this pattern is given by this, maybe here. And this is given by Japanese one, and this is given by probably here. I forgot it. But anyway, so this is not enough, I should say. So we have to think about more appropriate model. That is my business. Okay. Okay. Then coming back to experiments. You can see, so this cluster doesn't move, just stay there, almost stationary, okay? But this group is moving, and this is splitting, and to make a new cluster. So, when I look at this movie, or this snapshot, I said this same story as before. Bacteria possesses internal state of two phases, active, this one, and less active here. But less active is just stay there, okay? As far as the observation of experiments. So, and actual cells and less actual cells convert one another depending on their environment. This is ansatz, okay? And U and W is conversion like this, okay? This is also same story as the previous model. Of course, at last I did I did something in the previous model. That's why I could, attack this problem. Okay. So, and also, only active cells, say U, are moving, growing, and secret chemical attractant. On the other hand, less active cells, W, do nothing at all, just convert. And then we introduce 4 variables, U, W. This is probably same as before. And N's nutrients the same. And C is attractant, okay? This is a new one. Okay? And then so equation the following. Okay, so this is equation. And so here is the same one. But we put only the here. And so U convert to W. And the conversion rate is really depend on the nutrient. What that means? Wait a second. Okay. So if nutrient is quite low, so it's not good environment for bacteria. That might U convert to W. Okay, but if N is very big, so very nice condition, nice environment, that's why U doesn't need to convert from U to W. So that means A of N is a monotone, decreasing, okay? Monotone decreasing, that is our assumption. Okay? But the note, the model reduced to the 3-component system. I told you. So in the first 3 systems, they don't have any W. That's why. So if you can solve this system and then putting U and N in this term, and then you integral from 0 to T, then you can get W, okay? And this, okay, so G of U is a sort of the non-negativity monotone increasing, or A of N is the monotone decreasing. I just explained here. And alpha N here, alpha N is positive monotone increasing. But now, so I didn't check precisely, but only that this is our system, basically. And W is kind of, I mean, another equation. Okay. So, this is the initial boundary value problem. We consider this equation in omega. And of course, omega is just a convex domain. So, usually in our case is a square domain. And this is initial condition. Okay. And this is boundary condition. And this is I mean the initial condition of W. So W equals 0. What that means? So when you put E. initially on the surface of agar, at that time we put just only the fresh means the active one. Okay. So initially less active is 0. Okay. This makes sense from biological requirement. Okay, and so at first we have to do mathematics. So mathematics is the following. At first, local existence. So you are not interested, but so this is the first step to do in a mathematical way. And quite recently, so I mean this is Slovakia's group, and also France and myself showed a sort of showed some local existence in some norm. But why I said local? This system, in some situation, we may have blow-up phenomena. Okay, of course, in higher dimension, in higher dimension, in one dimension, we don't have any blow-up. In fact, this paper discusses about the 1D case. So 1D case, we have a global solution as well as attribute behavior. Attribute behavior is the following. So U, active cell, tend to 0, not surprising. And C is a chemical attractant, also 0, because U secret C, that's why. So this is 0. And N tend to some constant here. So it's a very, a nice result for 1D case. And also yes, and also this function the monotone decreasing, but we assume this is positive one. That was sort of the exponential decay. That's why we have this kind of convergence. And then there is some W infinity of X, such that W tend to W infinity. So this is almost perfect result for 1D case. How is a higher dimensional case? This is we have to carefully analyze. So this is very weak result. If the solution globally exists, so if we have no blow up, then we have the same result. It's very weak. And then this same thing. That's why we have the following, so U plus W, this is the total density of cells. So U tend to 0, the W tend to W infinity. So this is a sort of the final spatial pattern of colonies in population level. Okay? And the question is, how is the spatial profile of W infinity of X? And in the previous talk, I emphasized about the difficulty to know the spatial profile of W infinity X. Same story happened in this model. Okay? Therefore, we have to rely on numerics. Okay? Okay, so at first we have to assume that some specific function on G of U and chi and also alpha. Okay, and in this case, G is so like this. And I have to, sorry, I just forget to tell you an important, biological important thing. Why they want to aggregate? The reason is that this E. coli is so much damaged by oxygen. Okay, if the oxygen is just put in some oxy in the agar, okay, then they die. But some special E. coli which Badri and bug have, they produce chemotaxis attractant, and then they can aggregate, then they can survive. Understand? So for this E. coli, aggregation is very, very important. Okay? And then, where is that choke?
There are too many. The problem is which one is the good one.
Okay, so just okay. Okay, so if here is not so many. I mean, the audience here, and if each of them have some oxidized stress, for instance, so everybody die. But if you have a chance to make a group, sort of aggregation, okay, then you may survive. Okay. And there's an important, the good thing is a very what was oh yes, good. Okay, if you make only one very big spot, if you make it, so it's very good in order to survive. But on the other hand, nutrients only coming here. Only nutrient is have a chance to take a nutrients only this one. Inside is almost impossible. Okay, so this is not so good in order to survive. Of course, it's very good for oxygen storage. That's okay. Then it's better to very tiny one. Then it is easy to get the nutrient, but it's not so good for stress, oxidized stress. Okay. So it's very clever. They are very clever. They have a sort of very nice cluster. This is a micro cluster, and they, I don't know. So it's sort of very nice. Confederation, I don't know, so something like that, okay? So they did this kind of very clever, strategy, okay? That's why, so in this case, if, this growth rate is very low, so, so the growth rate is damaged by the, the oxygen, that's why it's quite low, and they increasing, so something like that, okay? This is anyway. Anyways, and here this is also very much difficult. If look at only the single cell, so experiments say the following: that this is sort of the here. This is sort of monotone decreasing. If C is increasing, then this becomes smaller and smaller. This is a sort of experimental support, but that is coming from a single cell. But in our model, we don't use this one. We use this one. What does it mean? This means now we are thinking about the population size. It's a macroscopic model. So many. So this is not necessarily monotone. This is like optimal. Optimal means is in a suitable concentration, then chemotaxis effect is stronger. This is the same one. We use this one, but we have no experimental support because this is almost 10,000 or 1 million. But experiments only checked it 1 or 2 or at most 10 cells. Okay. So they don't say anything about the population size. Only the small, look at this one like this. So it is very good for a single cell. But for populations levels, so many cells, nobody knows what kind of this one. So from mathematical motivation, so if I say very long story, but mathematically we suppose this is very good. If you're interested, I will explain later. Okay, anyway. Okay. And then forget this sort of the parameter here. But put it in a slide, so maybe you know. Okay. And then at first this is nutrient is relatively smaller. But this nutrient which implies a weaker chemotaxis effect because this is low means bacteria, the number of bacteria is quite low. So it means bacteria secrete the chemoattractant. That's why if N0 is small, it means like a proportion of the concentration of chemoattractant. Okay. And at that time, so this is just ring, like this. But please think about Tx is given by the 0T A N tau x U tau x d tau. Okay. So W is given by the this function and times this function. But basically this is. So this is sort of the history of U. Basically, of course we have this one, but basically. So this is the U. And how is the result of pattern W? So it's just I told this one. Then you can imagine this one. Just sort of the history, accumulation of U. So maybe you can imagine. Okay. And so how about when N0 is not increasing? So in experiment we have from this to this one. Okay, we know. And then at that time, the important thing like a transient behavior. This is very important. Okay, so it's a sort of a group, and some group is moving here, and then to make a new cluster, and but moving so like this. Okay, so this is really transient behavior. And then I will show. I hope this works. Yes, this is U. So this is W, U plus W. Okay. So this U is moving here and disappear. Disappear is this is W. Okay. So U is moving this way, but W is left there. So in my models, okay, so such one cluster, active cell is moving this way, less active cells stay there. And then they show this kind of pattern. Okay? Okay, so this kind of pattern. Okay? And how about the case when N naught is a little bit increasing? Then almost similar, but you can see very irregular or very chaotic pattern of spots. So it's very nice, but sometimes it's very irregular. Okay. So here we don't have any nice pattern. Okay. But if we change a little bit N0 from 1 to 1.3, maybe also maybe here. So we have very nice ordered pattern. So it means in experiment we have two different patterns, but intermediate probably it's a very strange pattern occurs. But this model shows the following. This is in transient pattern, okay? When n naught is 1, but for n naught is 0.8 or 1.3 is a very nice pattern, okay? So this is very nice hexagonal pattern. Okay, so maybe okay like this. Let me just skip. Okay, so now I have 8 minutes. So this is final one. Okay, this is final pattern. Do our model generate chevron-like pattern? This is a very hard problem. But now it's not so hard. But at that time, very hard problem. And wait a second. Okay, maybe I just skip here. Okay, and this is a kind of a numerics. Okay, but please trust me. Which parameter? Okay, here parameter we specified, and this is no meaning. Okay, just this indication of the radial symmetricity. So you may forget it. Okay. And this is a sort of okay. This is almost 1/4. Okay, and this is a sort of initial inoculation here. And this is active cell. This is less active cell. Okay. At first, I will show this one. So it's very strange. And the higher higher density is red, and the lower density is like blue here. So it's very strange pattern. But stop here. But it's basically this is almost ring. But on the ring, it's very like this. It's very much. Okay. But how was the pattern of W? But you know, also W is given by this one. It's easy. Just you think about the history or accumulation. Can you do that? It's very not so easy, but mathematically it's easy, just accumulation. So gradually you can see a sort of the chevron pattern. This is just the accumulation of this one. And if you look at that pattern in a more wider the domain, so I will show. Like this, okay. So this is a chevron pattern. And then, at first, honestly speaking, at first I thought probably this kind of pattern changed to like a style-like pattern, okay. And everybody tried to propose this kind of pattern. But in our model, is just this almost disk. Inside is you can see like this, okay. And I asked, the Badlin, one of the experiments, could please show me the transient pattern. And she showed me is like this. So this is really same thing. Inside is like this. But the global picture is like this. But okay, anyway, 6 minutes. Why I could produce this pattern? So this is the next problem. This is not by chance. Okay, what is the mechanism to generate chevron pattern? And then you can see this is of course chevron pattern, okay, here. But here is a maybe you can see is maybe it's not so easy. Can you see this checkerboard pattern? Maybe not so easy. Anyway, okay. Anyway, I will show the following. What does this mean? This is very much artificially initial. The shape of the function u naught of x is artificially make a diamond symmetric shape. So what does it mean? It's so like this, and so this is sort of symmetric lines, two lines here. So this is this one. Okay, this is very much artificial. No experiment. There are no experiment. Okay, only the artificially. Okay. So, so probably this is a symmetric, and this is also symmetrical pattern. And then we calculate. So you can see as kind of symmetric here, okay, and also symmetric. So as that is not ring, but sort of maybe may stop. Yeah. So this is almost straight line, okay, almost straight line. Okay, and how about here? So this is a sort of polygon shape. And you can see, and this is very nice regular pattern, okay, in this way. Also here, okay, also here. It's very nice, checkerboard pattern, okay. And on this line, it's a sort of the dislocation of crystallized pattern. So this dislocation showed us the appearance of chevron pattern. What does it mean? This is my guess. They don't like to make this kind of pattern. They prefer to make this pattern. But from one point inoculation, that's why so everywhere like this. So there has to occur such a dislocation everywhere. Okay, 1 minute. Okay, then so this is sort of the anyway. Okay, so this is a checkerboard. This is the diamond shape initial condition. This is the crystal structure, and here is a sort of dislocation. But in crystal growth, we can say defect of crystallization over grain boundaries in engineering side. And that's why very stable regular checkerboard pattern exists. which grows to some direction, okay? And like a grain boundaries shows a kind of chevron pattern, okay? Anyway, so this is just, the checks the why this system has a checkerboard pattern in the rectangular domain. And then this is a result, a final message. Bacteria, they like to make this pattern. This is very important. But we showed such pattern from the one point inoculation. That's why it's everywhere like this. And also we have a spatial fluctuation there. That's why you can see a sort of the chevron pattern everywhere. But so bacteria do not generate chevron-like pattern, but they do crystal structure pattern in a self-organized way. So this is a sort of message from modeling, the side to the biologist. At first, biologists or other people, they are very surprising to show this kind of pattern. But our model, if our model is correct, our model says that no, this is not surprising. Only they want to show this kind of pattern. And from one point inoculation plus spatial fluctuation generate this kind of pattern. Okay, so sorry. So now I just say a few words. Of course, there are many mathematical unsolved problems. One is also existence and blow-up problem for the unknowns UNCs like this. Still, we have to think about that. Okay. And also assumed behavior. Okay. In 1D, okay, but in higher dimension case, we have not yet done. And also, we want to know the the profile of W. So W is given by this one, okay? Oh, sorry. So I showed some mathematical model, and also I showed only the numerical simulation. But the important thing is to do analyze in a mathematical way. But today's lecture and yesterday's lecture, unfortunately, or I apologize you, so we have not yet showed a satisfactory mathematical result. Only the numerics. So please, you are interested, please come to my field. Okay. Sorry, 3 minutes over.